Greetings, my name is Michael Duda, and in this talk we're going to look at some of the advanced features of the WRF preprocessing system. This talk assumes that you have some familiarity with the WPS, so if you haven't already done so, it may be worth going back and checking out the fundamental capabilities of the WPS lecture, as well as the how to run the WPS lecture. So in about the first 40% of this talk, we'll look at a file called the GEOGRID.TBL or GeoGrid.TBL File. We'll see how this file is used by the WPS, and to spoil the surprise, this is the file that you might want to edit if you intend to ingest new sources of static terrestrial data through the GeoGrid program. So after we talk about bringing in new sources of static data, we'll look at a couple of examples of bringing in new high-resolution land use data and topography data through this GeoGrid.TBL file. In about the second 40% of the talk, we're going to look at a file called the METGRID.TBL or METGRID.TBL File. So we'll see how this file is used by the WPS, and we'll see how its role differs from that of the GeoGrid.TBL File. After we talk for a little bit about the METGRID.TBL File, we'll look at one detailed example of how you can make changes in this file to define how a new meteorological field is interpolated by the METGRID program. There's a second example that's included at the end of this lecture without narration. In the last 20% or so of this talk, we'll look at how we can use a utility program that's distributed with the WPS to solve a problem that we call the hot lakes problem. So starting right in with the GeoGrid.TBL or GeoGrid.TBL file. The GeoGrid.TBL file is a file that's used by the GeoGrid program to determine which static fields it needs to interpolate to your model domains at runtime. And that is the key here, that if you make changes to the GeoGrid.TBL file, you don't need to recompile the code. You can just rerun the GeoGrid program. So as we'll see in the next slide, there are different entries in this GeoGrid.TBL file, and each one corresponds to a data set that has to be processed by the GeoGrid program. So if you have new sources of data, or even if you want to adjust the treatment of existing fields, you may want to go in and make changes to this GeoGrid.TBL file. But as we saw in the How to Run the WPS lecture, in general, you don't need to edit this file when running the GeoGrid program, because the default entries are suitable for initializing a basic WRF simulation. So if you were to open up this GeoGrid.TBL file with your favorite text editor, you'll see that it's just a simple text file. And inside this file, we have different entries that are separated by at least 5 equal signs. And within each entry, all we do is we assign values to keywords. And you can look in Chapter 3 of the ARW User's Guide to see a list of all possible keywords that can be specified in a GeoGrid.TBL file. But in this example entry here, we're illustrating the most important keywords. So the name keyword gives the name of the field that will be produced by the GeoGrid program, and that's the field that's described in this entry. The priority keyword allows you to prioritize among different sources of data for the same field. In the typical case, we just have a single source of data for a field, in which case the priority is always set to 1. Dest type or destination type tells the GeoGrid program whether the field to be interpolated is a continuous field that can take on any real value or a categorical field that can only take on integer values. ZDIM name is used if you're processing a field that has multiple levels, which we call the Z dimension for the variable. Interp options specifies different interpolation options that the GeoGrid program should try to use when interpolating the field onto your model grid. And abs path is the absolute path of the data set to be interpolated on the file system. Instead of an absolute path, it's also possible to specify a relative path with the rel path keyword. This relative path is relative to the geographical data route that you specify in the nameless.wps file. So thinking back to the entry in the previous slide, we can use the GeoGrid.TBL to do a few things. So we could obviously go in and make changes to the interpolation scheme that's used for a field just by changing the setting of that interp option keyword. If you check in Chapter 3 of the User's Guide, you'll see that there are different keywords to apply smoothers to continuous fields. This can be helpful, for example, to smooth out high wave number components of the terrain field that's used by the model. And it's also possible to derive some fields from others. For example, if we have a data set that provides the fraction of every pixel that's represented by different categories, we can have the GeoGrid program derive the dominant category in every model grid cell using keywords in the GeoGrid.TBL file. But by far, the biggest use of the GeoGrid table file is to specify new sources of data that the GeoGrid program should interpolate. So if you set out to process a new source of data through the GeoGrid table file, the first thing that you need to do is to determine which of these three categories that data set fits under. So the first possibility is that you're processing a completely new field. This is not an alternative source for an existing field in GeoGrid, but a completely new field that we've probably never seen before. Typically this happens if you're doing some sort of development in the WRF model and you need an additional field to support that new scheme in the model or whatever it is you're developing. The second possibility is that you have a different resolution or different source of data for an existing field. And the key distinction between the second class of data and the third class of data is that in the second class, this new resolution or source of data does not need to be supplemented by any existing data. In other words, this data set can completely cover your entire model domain. So for example, if we had higher resolution topography data set and we could download an entire globe of data, that's an example of a field that could cover our entire model domain and therefore doesn't need to be supplemented. And that's in contrast to the third category of data, an alternative source or resolution for an existing field that must be combined somehow with existing sources. So for example, we might have a new soil category data set, but it only covers South Korea, while we intend to run a simulation over Southeast Asia. So if our new data set falls under the first category, a completely new field, then the thing that we need to do is to edit the GeoGrid table and add a completely new entry. So the important keywords to specify in the new entry firstly are name. So we need to give a name to the field that will be produced in the GeoGrid netcdf output. In this case, we've called it my new field name, but you should choose something better. Typically, we have just a single source for this new field, in which case the priority should be set to 1. And then we need to indicate whether this is a continuous or categorical data set. And then finally, as we discussed earlier, we need to specify the path of our data set on the file system and how we want the GeoGrid program to interpolate this data onto our ARW model grids. If our data set falls under the second class of new data, a different resolution or source that can completely cover our model domain, then in this case what we want to do is to open up the GeoGrid table file and find the existing entry for that field. And to that existing entry, we just need to add two keywords. We need to specify the path of our alternative source of data and how we want to interpolate our alternative source of data. You'll notice it in this example that we've provided a name here, myres, with a colon before the interpolation option and before the data path. We'll see in one of the examples how we can specify that we want to use myres of topography data rather than 30s resolution data. So the key here is that we need to give a mnemonic or name to our new resolution of data. And lastly, if our data set falls under the third class, it's an alternative source of data that needs to be combined with existing sources of data. In this case, what we need to do is to duplicate the existing entry for that field. So for example, if we had a higher resolution topography data set, but it only covered part of our simulation domain, we would need to duplicate the entry in the GeoGrid table file for HGT_M, topography height on the mass staggered points. In this case, we assign our new source of data a higher number priority. And this is a bit counterintuitive. Typically, we think of priority number 1 as being the highest priority data, but in the case of the GeoGrid table file, higher numbers mean higher priority. We also, again, need to specify whether this is a continuous or categorical data set, and we need to provide the path of the data and how we want to interpolate it. If we have just a single source for this higher resolution data, we don't need to choose any special name. We can simply call it default. So having talked about the different changes that we can make to the GeoGrid table to ingest the new source of data, we can summarize the complete process of bringing in new static terrestrial data sets through the GeoGrid program in 3 steps. So in the first step, we need to prepare our data set into a file format that is understandable by the GeoGrid program. In Chapter 3 of the ARW User's Guide, there's a section entitled Writing Static Data to the GeoGrid Binary Format, and that provides more details on this file format. We'll also cover the file format in the next few slides. If you'd like to see some example C code for reading and writing this binary format, you can look inside the WPS source code, and find a file called read.geogrid.c and write.geogrid.c. Once we've written the data into a binary format that the GeoGrid program can understand, we also need to prepare a metadata file, which is always a text file called index. This metadata file tells the GeoGrid program about the coverage, the spatial resolution, the projection, the type of data, and how many bytes are used to represent each value in our data set. This index metadata file is always saved in the same directory as the data itself. And that is the directory that we specify in our GeoGrid table entries. And then lastly, once we've prepared the data and metadata, we can edit the entry in the GeoGrid table file as described in the previous slides. Now, the binary data format that the GeoGrid program can understand is a simple binary roster format. And so you can imagine taking your data set and putting it into a rectangular array in memory, and then writing that array out column by column and row by row to a file, without including any sort of header information and no record markers of any kind. So for example, if we had a data set that had 6 columns and 8 rows, by convention we begin writing out the southwest corner first, and then we progress across columns, writing them each out to the file, and progressing through the rows until we finally write out the last column of the last row in our rectangular array. So as a consequence, if we have a data set that has n columns and m rows, and we've used k bytes to store each value on a file, then the size of our file should be exactly n times m times k bytes, again because we have no header information of any kind. And this seems like an obvious point, but it's always worth checking. If you're a Fortran programmer, it's worth noting that when writing out binary files with Fortran, you have to take care to write the files as, for example, stream access files. By default, Fortran uses record markers when writing out records, and the GeoGrid program will interpret these record markers as actual values in your array. As an alternative to writing out these files directly from Fortran, you can use the C routines read.geogrid and write.geogrid to read and write binary files of data. If you're comfortable working in Python, you can easily read and write binary files that are usable by the GeoGrid program using NumPy. You can use numpy.from file to read one of these binary files into a NumPy array, and you can use array.to file to write an array into a file that the GeoGrid program can read. It's important to note that all of the values in these binary files are represented as integers, so you'll need to use dtype to cast a NumPy array into an integer typed array before writing it out to a file. In addition to a particular file format, the GeoGrid program expects a particular file naming convention for all binary files of data, and that convention is 5 digits, hyphen 5 digits, dot 5 digits, hyphen 5 digits. This first set of digits represents the starting X index of the data contained in the file, and the second set of 5 digits represent the ending X index, and these are 1-based indices that we'll see an example of in the next slide. The third set of digits represents the starting Y index, and the last represents the ending Y index of the data set contained in a file. In the simple case that we have just a single tile of data in our data set, for example, if we had a data set with 500 columns and 750 rows, we might then just have a file that's named 00001 -005000.00001 -00750. This file naming convention becomes useful when we want to take a large data set and split it up into tiles. So if a data set is split into tiles, all of the tiles need to have the same X dimension. In other words, they need to have the same number of columns, and all of the tiles need to have the same Y dimension. In other words, they need to have the same number of rows. However, the X and Y dimensions can be different. If you happen to have a data set whose number of columns isn't evenly divided by some other integer, you can simply add padding columns onto the data set. And whatever padding value you use can be specified in the metadata file as a missing value. So for example, if we wanted to take a data set and split it up into 4 tiles, each with 1,480 columns and 1,600 rows, we might have 4 files for our data set, named as shown here on the right part of the slide. So if you're working with a data set that neatly fits into a rectangular array, then everything we just talked about sounds straightforward. But what do you do if you have a data set that doesn't neatly fill up a rectangular region? Let's say, for example, that you have volunteers who have gone around an urban area and taken measurements of sky view factor. In general, this urban area isn't going to be a perfect rectangle, so we need some way of fitting this data set into a binary file. The idea is that you first need to discretize this data set onto a regular grid, and then you can store that discretized data set into an array that minimally encloses the data set. And for all the pixels of this array that contain no data or missing data, you can fill those in with some missing value of your choice, but whatever value that is, you'll need to indicate it in the index metadata file for the data set. So now that we've talked about how to prepare data sets in a format that the GeoGrid program can use, and we've talked about the changes that we need to make in the GeoGrid.TBL file in order to get the GeoGrid program to use our data set, we'll look at a couple of examples of introducing new land use data and new topography data. So in the first example, we're supposing that we're running a high-resolution simulation over the Gulf Coast centered over the city of Houston in the US state of Texas. So what we're showing on the left panel here is a plot of the land use index for our model domain. So this blue region represents the Gulf of Mexico, and this black colored area represents the city of Houston in Texas. And let's suppose that for our simulation, we have some new data set that only covers the city of Houston, the metropolitan area. And this new data set is not at a higher spatial resolution. It's still at 30 arcsecond resolution, but it has additional urban categories. So rather than a single homogeneous urban category, our new data set provides urban categories 31, 32, and 33 that might, for example, represent residential areas, commercial or high-intensity residential areas, or industrial areas. So this data set, as we said, just covers the Houston metropolitan area, and it might be as shown here in the right panel. So these blue pixels represent one of these three urban categories, 31, 32, or 33, and these white regions represent missing data. In other words, it's not urban, so we don't know what it is. So what we would like is to be able to map this new Houston data set onto our model domain to get a more accurate representation of the city of Houston. So we've already talked about how to write data sets into the proper binary format, so we'll assume that we've already done that. The second step that we haven't yet talked about is how to prepare an index metadata file for our data set. And we have an example metadata file here on this slide. So the index metadata file is just a text file that you can edit with your text editor of choice. And much like the format of the GeoGrid table, we assign values to keywords. So we need to tell the GeoGrid program in our metadata file that this is a categorical data set. It contains categories from 31 to 33. The data are projected on a regular latitude-longitude projection with delta x and delta y values of 30 arcseconds, or 1/120th of a degree. And we know that the 1 pixel, i.e. the southwest pixel of our data set, is at latitude 29.33 and longitude 95.996 west. Word size tells the GeoGrid program how many bytes we've used to represent each value. In our case, we just need to represent three values, 31, 32, and 33, so using a single byte to represent those values is sufficient. We're also telling the GeoGrid program that we have a single tile of data with 157 columns and 143 rows, and where we don't have urban data, we've put in a missing value of 0. Units and description are nice to add to a metadata file, but they aren't actually used right now by the GeoGrid program. So after we've prepared our data set and prepared an index metadata file for our data set, we can then go in and make a change to the GeoGrid.TBL file. In this example, our Houston dataset falls under the third class of new data. It's an alternative source for an existing field, but it needs to be supplemented with the default dataset because our Houston data only covers part of our model domain. So in this case, we're going to make a duplicate of the land use F, or land use fraction entry in the GeoGrid.TBL file. And we're going to assign our new entry a higher priority number, a priority number 2. And of course, this is a categorical data set, and if we were to write out the individual fractions of each category, we might want to give a name to that layer dimension of landcat. Lastly, I've prepared this dataset and put it in my home directory /user/tuta in a subdirectory called Houston, and I'm telling the GeoGrid program that I want to simply map these values onto my model grid using a nearest neighbor interpolation. So after we go through those steps of preparing the data and metadata and making a new entry in the GeoGrid table file, we can rerun the GeoGrid program without recompiling the code. So on the left, this is what our domain looked like using the default land use data, at least the default prior to version 3.8 when this slide was made. And on the right, we see an example of what the land use field looks like after making those changes. So these orange and pink and red colors represent our 3 new urban categories, and you can see that they've been mapped onto our domain exactly where our data set covered. And outside the coverage of our new data set, we get identical land use values to the previous domain. So as another example, we're going to suppose that we're running some high-resolution simulations that nest down to 111-meter resolution over part of the city of Seoul. So because the default data set that we provide for topography is at 30 arcseconds of resolution, that's about 925-meter grid spacing at the equator, that's certainly a sufficient data set for our outermost 1-kilometer domain in the simulation. But as we nest down at a 3-to-1 ratio to a 333-meter grid and nest down further at a 3-to-1 ratio to a 111-meter grid, we might want to try to find some higher resolution topography data to better resolve the details of the hills in and around the city. There is a nearly global data set of topography called SRTM, the Shuttle RadarSat Topography Mission. That's available at 3 arcsecond resolution, which is about 90-meter resolution. So that's certainly sufficient to use for domains 2 and 3 in our simulation. And note that this new data set, because it can completely cover our simulation domain over South Korea, falls into the second category of new data. It's a higher resolution or alternative source of data that can completely cover our model domain. So in this case, what we need to do is to firstly prepare our data set into a binary format. This turns out to be easy to do in the case of SRTM, which is provided in GeoTIFF format. Using something called the Geospatial Data Abstraction Library, GDAL, we can easily convert GeoTIFF format into the binary raster format that's used by the GeoGrid program. Once we've converted our topography data into the proper format, we can create an index metadata file for the dataset, and then we can go in and find the existing entry in the GeoGrid table file for the topography height field. This is called HGTM. In this case, we just need to add a new path to our SRTM topography data, as well as an interpolation option, which we've just taken as a 4-point bilinear interpolation. The last thing that we need to do in order to tell the GeoGrid program to use SRTM topography data rather than the default topography data is to specify in our nameless.wps file the following for the geog.datares nameless variable. So for domain 1, we can leave that variable set to default, and that will tell the GeoGrid program to use the default dataset, which happens to be this GMTED 2010 30 arcsecond dataset. But for domains 2 and 3, try to find a resolution of data that's called SRTM in every entry in the GeoGrid table file and use that. And only if a resolution called SRTM is not found should the GeoGrid program try to use a resolution called default. And this might happen, for example, for the land use data, for which we don't have a resolution called SRTM. And similarly for domain 3. So after making these changes, we can rerun the GeoGrid program, and on the left, we see the topography data interpolated from the 30 arcsecond GMTED 2010 data set, and on the right, we see the topography data set from the 3 arcsecond SRTM data set. So hopefully, this better resolution of the hills in and around the city might improve our simulation. And finally, as a one-slide example, just because it looked interesting, let's suppose that we're running some very high-resolution simulations over the city of Los Angeles in California. And let's suppose that our inner model domain goes down to several tens of meters of resolution. And you can see on the left that by default, at least with the old USGS land cover data set, the city of Los Angeles looks like a big homogeneous urban area. For the continental United States, there is a high-resolution data set of land use data called the National Land Cover Database, NLCD, that provides data at 30-meter resolution. So what we've done is to download the NLCD data for the region that's covered by our domain, and we extracted just the urban categories, as we did in the Houston land use example. And you can see that by introducing this new land cover data into our model simulation, we can now pick out different parts of the urban area. So now we'll turn our attention to the METGRID.TBL file, and we'll explain how this file is used by the METGRID program, and we'll look at one detailed example. So the METGRID.TBL file is a text file that tells the METGRID program how to horizontally interpolate fields that it finds in intermediate files. And this is in contrast to the GEOGRID.TBL file, which told the GeoGrid program which fields had to be found on disk. So the METGRID.TBL only tells the METGRID program how to interpolate fields if they are found. And by default, the METGRID program will process every field that's found in an intermediate file. And crucial to the example that we're going to look at, if the METGRID program encounters a field in an intermediate file, and that field does not have an entry in the METGRID.TBL, the METGRID program will use a default interpolation scheme, which is a simple nearest neighbor interpolation. It's also worth noting that if you have fields in intermediate files and you don't want them to be processed by the METGRID program, you can add a keyword to an entry for those fields in the METGRID.TBL to say that those fields should be discarded. And because the METGRID.TBL file only tells the METGRID program how to process fields that it finds in intermediate files, rather than which fields to process, we've tried to provide entries in the METGRID.TBL for just about every meteorological field that we've been able to use when initializing a model simulation. So as a consequence, it's unlikely that you'll need to edit the METGRID.TBL except in cases where you're bringing in new sources of meteorological data. Of course, if you like, you can go into the METGRID.TBL and edit the existing interpolation options for fields. And you can even have the interpolation option depend on the source of the meteorological data. So here we see an example entry in a METGRID.TBL file. So the format of these entries is very similar to the format of GeoGrid.TBL entries. Each entry is separated by at least 5 equal signs, and within each entry we assign values to keywords. So this name keyword tells the METGRID program that this entry applies to any field in an intermediate file that is named SM000010. In other words, it's the soil moisture in the 0 to 10 centimeter layer. The interp option keyword provides the METGRID program with a sequence of interpolation schemes that it can try to apply to the field. And we'll see how this works in our first example. The mask keyword tells the METGRID program whether this field should be interpolated to land or water points. And the interp mask keyword tells the METGRID program that wherever the land sea field for this dataset is 0, in other words, wherever the land sea field is a water point, we shouldn't use the corresponding values from the soil moisture field because they're likely to be invalid. The fill missing keyword tells the METGRID program to fill in any points in our model domain where we couldn't or didn't interpolate a value for this field, for example, because those points were water points. And the flag and output keyword simply tells the METGRID program to write a global attribute to its netcdf output to communicate to the real program that this field was found. So that's essentially it. The METGRID.TBL is a file that tells the METGRID program how to interpolate fields. So what we're going to do now is to look at an example of how we can use the METGRID.TBL to describe a masked interpolation to the METGRID program. So in this example, we're going to assume that we've set up a 500-meter model grid with 1,000 by 1,000 grid points centered over the city of Houston. And this is in fact the same domain that we had used in our Houston land use example when talking about the GeoGrid.TBL. So we'll assume that our meteorological data come from the 1 degree GFS, and it's important to note before looking at the next slide that we're interpolating 1 degree data, which is something like 111 kilometer grid spacing around the equator, onto a 500-meter grid. So there's about a factor of 200 difference in resolution between the GFS data and our model grid. And for this example, we're going to suppose that we didn't already have a METGRID entry for the soil moisture field in the 0 to 10 centimeter layer. So if our intermediate file had a soil moisture field, but our METGRID.TBL did not contain an entry telling the METGRID program how to interpolate that field, when we run the METGRID program, we would get this message printed to the log file and also to the terminal screen. And it would say, entry in METGRID.TBL not found for field soil moisture 000010. Default options will be used for this field. And you may recall that the default interpolation option is a nearest neighbor interpolation. So what we're looking at here in the lower right part of the slide is the resulting soil moisture field. And you'll have to use your imagination, but these blue points here represent the Gulf of Mexico. Houston should be right around here. And you'll notice that this field looks very blocky. It turns out these squares in our model domain are about 1 degree by 1 degree. So to every model grid point in this area, we've simply interpolated from the nearest GFS grid cell. So the soil moisture field that we saw on the previous slide is completely unsuitable for use in our model simulation. And that message that was printed to the terminal screen is our indication that we should create an entry in the METGRID table for the SM000010 field, which we'll refer to as soil moisture from here on out. So using our text editor of choice, we can open up the METGRID table and create a new entry. So we know that the name keyword should be set to SM000010 because we're creating an entry for the soil moisture field. We can set the mask keyword to water to tell the METGRID program that we don't need to interpolate the soil moisture field onto water points as dictated by our high resolution GeoGrid land sea mask. We can add this interp mask keyword to tell the METGRID program that wherever the GFS land sea field is 0, that represents a water point, and we should therefore not use the corresponding pixel in the soil moisture field from GFS because it's likely to be invalid. We can specify a set of interpolation options to try, and we'll illustrate this on the next slide, but the idea is that wherever possible, the METGRID program will first try to use a 16-point interpolation stencil, and if for some reason that doesn't work, the METGRID program should just use a nearest neighbor interpolation. And then lastly, over any points where we couldn't or didn't interpolate a value, just fill those pixels in our model grid with a value of 0. So for example, we should expect all water points in our model domain to be filled in with a value of 0. So after adding that entry to our METGRID table, we can rerun the METGRID program, and now that error message is no longer printed to the terminal screen because we in fact do have an entry for soil moisture. And after running METGRID, we can use NCView to take a look at the METGRID netcdf output. And if we look at the soil moisture field, we'd see something that looks like this panel on the left. So you'll notice that there are some parts of our model domain where the soil moisture field looks very smooth. And it turns out those are the model grid cells where we had a 4x4 grid of valid GFS data points around those model grid points. And so the METGRID program was able to apply a 16-point interpolation stencil. As we get closer to land sea boundaries in the GFS grid, you see that the soil moisture field starts to look blocky. And these are the points in our model domain where the METGRID program had to switch from a 16-point interpolation stencil to a nearest neighbor interpolation. And there are even parts of our model domain where the nearest GFS grid point was a water point, even though those points should be land according to our GeoGrid land sea mask. Now we can try to improve upon the interpolated results by adjusting the METGRID table based on a few observations. So firstly, there are parts of our model domain that might not have a 4x4 grid of valid GFS points, but some of these grid points here might have a 2x2 grid of valid GFS data surrounding them. So rather than using a 16-point interpolation scheme, as we get closer to land sea boundaries, we might be able to switch to a 4-point interpolation, which is basically a bilinear interpolation. And for some of these points in our model domain, for which the nearest GFS point was a missing point, perhaps instead what we could do is to interpolate or average from any of the surrounding valid GFS points, rather than simply taking the nearest GFS grid point. So based on those observations, we can go into the METGRID table and make a couple of changes to the interpolation options in our soil moisture entry. So where the 16-point interpolation could be applied by the METGRID program, it seemed that it worked pretty well. As we get closer to land sea boundaries, we might not have a 4x4 grid, in other words a 16-point grid of surrounding valid GFS grid points, but we might have a 2x2 grid of valid grid points, and that allows us to use this 4-point interpolation stencil, which is equivalent to a bilinear interpolation. And then as we get very close to land sea boundaries, rather than using simply the nearest GFS grid point, we can use this interpolation scheme called average 4-point, which takes an unweighted average of any of the 4 surrounding points to a model grid cell that are valid. And it's worth noting that this 4-point average will work anywhere the nearest neighbor would have worked, and in fact it will work in more cases. So after making those changes to the METGRID table entry for soil moisture, we can rerun the METGRID program, and our new soil moisture field looks like the panel on the left of this slide. So you'll notice that as we get closer to land sea boundaries, the field still looks smooth, and that's because as we couldn't use a 16-point interpolation scheme, we were able to switch then to a smaller interpolation stencil. And you'll also notice that there are no longer blocks missing from the coastline. And that's because for all of these grid points, we're able to take an average of any surrounding GFS grid points that were valid. And for this block right here, indicated by the laser pointer, it was probably the GFS grid point that sits right here. So there's one final improvement that we can try to make to our METGRID table entry for soil moisture, and that should help the interpolation along the coastline here. So we noted that the values of the soil moisture field looked somewhat blocky, and that's because for every one of the model grid points that lies within one of these regions, for example, the one that's being indicated by the laser pointer, we're simply taking an average, an unweighted average, of any of the 4 surrounding GFS points that are not missing. Rather than taking the unweighted average, we can switch to a weighted average. And we do that by using the WT, or weighted average 4-point interpolation option, in place of the average 4-point option. And by doing that, then we get what is probably the best soil moisture field that we're going to be able to get when interpolating from 1-degree data onto a 500-meter model grid. So in the final part of this lecture, we're going to see how we can use one of the utility programs that is provided with the WPS to solve a problem that we refer to as the hot lakes problem. So the hot lakes problem is one that you might encounter as you start to run higher resolution simulations with the ARW, and it's a problem that you might encounter particularly when running simulations during the winter months. The idea is that as you run at higher resolution, you'll start to resolve small lakes that are not resolved by the dataset that's providing your initial conditions. And this means, for example, that the METGRID program has to horizontally extrapolate to those lakes to get values for sea surface temperature. And oftentimes that horizontal extrapolation takes values from nearby water points that might in fact be resolved ocean points. And this leads to values for small inland lakes, for example, in the sea surface temperature and skin temperature field that are unrealistically warm. So in the example problem that we're going to look at for the next few slides, we're running some simulations over Iceland in the month of January, and we're nesting down to very high resolution over this Mývatn region. And on the right panel of this slide, what we're looking at is the skin temperature field, and we can see that there is this small lake, Mývatn Lake, that we're resolving in our simulation, and the lake temperature, at least according to the skin temperature field, is around 277 Kelvin. We believe that this is probably too warm this time of year. It's likely that this lake is frozen, and so we would expect lake temperatures to be somewhere closer to 273 Kelvin. This unrealistically warm lake gives off high moisture and latent heat fluxes, and so we'd like to find some way, using utility programs that come with the WPS, to provide a better value for the lake temperature. So the approach that we're going to talk about assumes that we're running at least WRF version 3.3, which by this time is probably a safe assumption. And the idea is that if we can tell the real preprocessor which water points are inland water bodies and which are ocean points, in other words, which points are likely to be resolved by the SST dataset and which are unlikely to be resolved, then as long as we can provide some better estimate for inland water body temperatures, the real program can selectively substitute that estimate for the extrapolated SSTs. So the first thing that we need is some land use dataset that distinguishes between lakes and oceans. The second thing we need is some way to create a proxy field to be used for the SST over just these inland water bodies, but not over oceans. And then the second thing we need is for the real program to selectively substitute that proxy SST field only over lake points. So the first challenge is distinguishing between lakes and oceans, and we need to do this through our land use dataset. It turns out there are some land use datasets that do have a separate water category for inland water bodies versus oceans. For example, there's a MODIS dataset that contains a lake category, and the Korean land cover dataset also contains a lake category. For other datasets, we at NCAR have developed an algorithmic method for identifying inland water bodies. So for, in principle, any data set, we could run our algorithm on that data set to identify lakes. It's worth pointing out that the default land cover data set in WRF version 3.9 and later is this MODIS land cover data set at 30 arcsecond resolution that does contain a separate lake category. So as long as you're working with a sufficiently new version of the WPS, there's nothing special that you need to do to get a special lake category. So if we're using a new enough version of the WPS, we don't need to worry about getting a separate lake category, and we can turn our attention to a method by which we can construct a proxy for the SST field to be used only over inland water bodies. The WPS provides a utility called average_tsurface.exe, which can be used for this purpose. What this utility program does is to compute a temporal average of the 2-meter air temperature, with the average being computed over some integral number of diurnal cycles, depending on the available intermediate files in your run directory. After this program finishes running, it writes output into an intermediate file format with a file name of taverage_surface, and inside this intermediate file called taverage_surface, we have a single field that's also called taverage_surface. This represents the pointwise temporal average of the 2-meter air temperature. So to illustrate the entire process then, after running the GeoGrid program, we get these geoem.d01, d02, d03 files, each of which has a land category dataset that has a separate lake category. After having run the ungrid program, we get a set of intermediate files which presumably have a 2-meter air temperature field in them, and once we have this set of intermediate files, we can run this average_tsurface utility to produce a new intermediate file that's called taverage_surface, and that contains a field called taverage_surface. Running the METGRID program, we can horizontally interpolate not only all of the fields in these intermediate files produced by ungrib onto our model domains, but we can also horizontally interpolate the taverage_surface field onto our model domains. And this interpolated taverage_surface field is written along with all of the other interpolated fields into the METGRID output. As we said earlier, newer versions of the RIO program are able to selectively substitute this taverage_surface field for the skin temperature and SST fields only over inland water body points. So we can now illustrate this in the context of our Iceland simulations. So on the left of the slide, we're showing our nested domain setup. Our outermost domain is at 16-kilometer grid spacing, and it covers the area around Iceland. We nest down to 4-kilometer grid spacing at a 4:1 ratio, and then you can see in domains 3 and 4, we nest down further over this Mývatn region, down to a grid spacing of 250 meters. And it's inside our domain number 4 that we can resolve this Mývatn lake, which is generally not resolved by the SST dataset that provides our model sea surface temperatures over the North Atlantic. So you may recall from a few slides back that when we originally ran our simulations over Mývatn Lake, we were getting a lake temperature of around 277 kelvins, which we believed was unrealistically warm for the month of January. After substituting the skin temperature over Mývatn Lake using the 5 previous days of 2-meter air temperature, we get a lake temperature that's around 273.8 kelvins, and we believe that's much more reasonable. So when we run our simulation, we can write out a time series from a point that's right in the middle of the lake, and for example, we can look at the sensible heat flux from that point. So the red curve in this plot represents the sensible heat flux that was measured in our model simulation when we used the extrapolated RTG-SST that was horizontally extrapolated from the nearest ocean point. And you can see that it's a positive heat flux. The green curve represents the heat flux when we substituted that extrapolated sea surface temperature with an average of the previous 5 days of 2-meter air temperature over the lake. And you can see that now we actually have a negative sensible heat flux. And the hope is that at least that somehow represents an improvement in our simulation. And we were able to do this by making use of one of the utility programs that comes with a WPS. So in summary, in this lecture, we firstly looked at both the GeoGrid table and the METGRID table, and we've got an understanding now of what these files do. We've seen some examples of how we can ingest new geographical data sources into the WPS, and the specific examples were high-resolution land use and topography data. We've also seen how we could use the METGRID table to correct interpolation-related problems that might arise when we introduce new sources of meteorological, either atmospheric or land surface datasets. And we've seen how we can make use of just one of the utility programs that's provided with the WPS to hopefully improve our simulation. For more information on some of the utility programs that are provided with the WPS, the next best resource to check would be Chapter 3 of the ARW User's Guide. There is also a web page that's probably out of date, but it may provide you some steps and pointers on how to introduce your own high-resolution topography and land use data, and that URL is given at the bottom of this slide. This concludes the main material of this lecture. In the remaining slides, without narration, we have another example of how you can use the METGRID table to selectively choose interpolation options depending on the source of meteorological fields.